Good morning, all of you. This is Keshwan from CSC Data Science Department from third semester, section B. Now, I am presenting the topic of discrete mathematics. Create a pre-processing module for a machine learning system that can map input features using invertible functions and relations. Here, now we go through the introduction. Pre-processing module for the machine learning by using of invertible functions. Here we use the invertible function for the pre-processing module, and also we are using machine learning. So why we use the invertible pre-processing in the machine learning? Here there are four reasons for the using of invertible pre-processing in the machine learning. The first one is preserving information and reversible data flows, enhanced interpretability, and critical for specific apps. When we go through the preserving information, here traditional pre-processing often loses crucial data, and invertible methods ensure every piece of information is retained, allowing exact reconstruction. And in reversible data flows, transformations can be mapped back to original inputs, crucial for interpretability and integration with advanced generative models. Next, enhanced interpretability. Here, by understanding how futures are transformed and reversed, we gain deeper insights into model decisions in critical for specific apps. Here, essential for applications requiring exact input reconstruction by directional mappings like medical imaging or security. So when we come to the preserving information, here traditional pre-processing, it must be losses the crucial data, and invertible methods ensure every piece of information is retained and allowing the exact reconstruction. Second, reversible data flows. In reversible data flows, transformations can be mapped back to original inputs and crucial for the interpretability and integration with the advanced generative models. Next, enhanced interpretability. By understanding how futures are transformed and reversed, we gain a deeper insights into model decisions. In the critical specific case, here only some of specific apps are mm, essential for applications requiring exact input reconstruction. So overall, the invertible pre-processing offers a significant leap beyond conventional methods, enabling more robust and transparent machine learnings. Now, core concepts. What are the core concepts in invertible functions and relations? First, invertible functions. When we come to the foundation of the invertible functions, bijective nature. Here, bijective means it can satisfy both the one-to-one and the onto functions. That is called as bijective nature. An invertible function is both one to onto function, guaranteeing a unique output for every input and vice versa. Here we can guaranteeing a unique output for input and vice versa. Next, lossless transformation. Here this property ensures that no information is lost during the future transformation process, making it fully reversible. Common transformations. Examples include affine scaling, linear transformations, invertible linear maps, and advanced techniques like coupling layers. This is totally about the foundation. First, bijective nature and lossless transformation. Here we can ensure that no information is lost during the future of transformation process. And common transformations. Mainly the common transformations are affine scaling and invertible linear maps and advanced technique like coupling layers. Next, extending to relations. Invertible relations maintain future dependencies and structural integrity during complex data mappings, crucial for high-dimensional and interconnected datasets. When we come to the relations, relations maintain future dependencies and structural integrity during the complex data mappings and crucial for high-dimensional and interconnected datasets. Next, building blocks. What are the building blocks and immutable layers in the pre-processing? First, coupling layers and affine coupling, invertible layers, and activation normalization. Coupling layers. These layers split input features into two parts. One part is transformed based on another, ensuring invertibility. This approach maintains a structural integrity while enabling complex nonlinear mappings. Next, second one, affine coupling. A prominent example as shown in the template, as the inverse function allows exact reconstruction and the scaling and translation functions can be complex neural networks. Next, invertible linear layers. These involve multiplying the input by an invertible matrix. The inverse operation is simply multiplying by the inverse matrix. This preserves linear relationships and can be used to decorrelate futures. Next, activation normalization. These layers perform invertible normalization of maintaining zero mean and unit variance. They can distribute remain stable across layers without error. So these are the some of the building blocks in the invertible layers. The first coupling layer is split into the two parts, and affine coupling. Here we have the one of the example of the inverse function, and it can allows the exact reconstruction. The scaling and translation functions are maybe complex neural networks. Next, invertible linear layers. In invertible linear layers, the involvement of multiplying by input by getting of the invertible matrix. The inverse operation is simply multiplying by the inverse matrix. Next, activation normalization. Here, the invertible normalization has been activated in this layer only. Next, invertible neutral network architectures. First, mint set and IRSNet's density estimation, efficient inversion, and unified architecture. These are some of the architectures of the invertible neutral network. First, mindset. Mindset utilizes masked convolutions and triangular Jacobians, enabling efficient inversion and precise likelihood computation for complex data distributions. Next, iris nets. Invertible residual networks modify traditional REST blocks to guarantee invertibility, allowing for deep invertible architectures without dimension splitting. Unified architecture allows a single model to perform classification, density estimation, and generative tasks, simplifying development. Density estimation. These networks naturally support density estimation, providing a probabilistic measure of input data likelihood. Efficient inversion. Optimized algorithms ensures that mapping is computationally futures deployment in real-world ML. So these architectures are represent a paradigm shift, offering models that are not only powerful but also fully reversible and interpretable. So this is all about the architecture. Now, practical pre-processing steps using invertible models. There are 5 steps in the pre-processing. First, step 1, affine standardization. Begin with the invertible affine transforms like modified standard scalar. This ensures futures are normalized while preserving the ability to the reserve scaling and translation parameters. Second one, nonlinear transformation. Here, apply invertible nonlinear transformations using coupling layers or other invertible neutral network components. These captures complex relationships in the data. Next, step 3. Linear correlation mapping. Integrate invertible linear layers to manage and transform future correlations. These steps can help decorrelate futures for downstream models. Next, step 4. Latent representation. Here, utilize trained invertible neutral networks to map raw inputs into rich invertible latent representation. These latent spaces are often more conducive to learning. Next, pipeline integration. Here, embed the entire invertible preprocessing module with your machine learning pipeline, rigorously ensuring consistent forward and inverse transformation. This is all about the practical pre-processing techniques in the using of invertible modules. There are 5 steps. First one, affine standardization, nonlinear transformations, linear correlation mapping, and latent representation, pipeline integration, and etc. Now go to the another slide. Advantages. What are the advantages over traditional pre-processing? Here, there are so many advantages of traditional pre-processing. First, exact future reconstruction and enhanced model interpretability, generative modeling support, robustness to outliers, and advanced application enablement. First, exact future reconstruction. Here, unlike traditional methods, invertible pre-processing allows perfect recovery of original futures from the transformed data and ensuring no information loss, and facilitates clearer insights by allowing direct tracing of model decisions and outputs back to the original input futures. Next, generative modeling support. Here, crucial for generative models and likelihood-based training, enabling the creation of new data points that resemble the original distribution. Robustness to outliers. By preserving the data's underlying structure, invertible methods often handle the gracefully than heuristic scaling. Next, advanced application enablement. Here supports the innovative applications such as model inversion, data analysis, and bias correction techniques. These are techniques used in this advanced application enablement. So these are some of the advantages in the traditional pre-processing. Next, go through the another slide. Example use case. Now we take an example of EEG signal decoding. Uh, so here we have taken the application of brain computer interface BCA. Noise, here application of brain computer interface BCI. Here noise robust classification. EEG signals are highly susceptible to noise. Invertible coupling layers can transform the signals into a more robust representation for accurate classification tasks. Visualizing discriminative features. Here, the invertibility allows researchers to map the transformed features back to the original EEG signal space. This reveals which specific brainwave patterns or features are most discriminative for a given task, offering crucial diagnostic insights. Improved interpretability. By understanding the exact transformation and their inverses, clinicians and researchers can be made better interpret the neural correlates of specific cognitive processes or neurological conditions. This enables more precise and reliable decoding of brain activity, advancing the both clinical diagnostics and BCA technology. No. So overall, how we implement this? So we need the tips and tools. First, leverage existing libraries, explore deep learning frameworks, enforce invertibility constraints, and validate inverse mapping. Integrate with pipeline frameworks. In leverage existing libraries for invertible affine scaling, skittle-learns a standard scalar can be adapted or specialized invertible modules can be used in PyTorch or TensorFlow. Explore deep learning frameworks. Many deep learning frameworks offers implementations or extensions for invertible layers. Next, enforce invertibility constraints. Here, during model training, ensure that invertibility is maintained. This often involves monitoring the Jacobian determinant to guarantee non-singularity. Invalidate inverse mapping. Rigorously test the accuracy of the inverse transformation on unseen data. A small reconstruction error is acceptable, but it should be quantified. Integrate with pipeline frameworks. Use tools like script team, pipeline, or custom wrappers to seamlessly integrate invertible preprocessing modules into your full ML workflow. Next. So now we conclude that unlocking the reversible future engineering. So by the using of invertible preprocessing models, here we can unlock the reversible future engineering. So we can reshape the machine learning by ensuring information preservation and enabling seamless directional mappings. This revolutionary approach bridges the gap between discriminative and generative modeling, significantly enhancing both interpretability and robustness across diverse applications. With the advent of powerful architectures like MintNet and IRISNet, practical and scalable solutions are becoming increasingly accessible. Embracing invertible reprocessing means future-proofing your ML systems with transparent, reversible, and highly efficient future transformations. So, we conclude that unlocking of reversible futures in the engineering. So, thank you for giving this an opportunity to present the topic of invertible functions pre-processing by using of machine learning. Thank you.